Hope all is going well. It's only the second week. I know some of your classes it's already kicked up in high gear, but I feel like this class has had a gentle first week, so now we'll start getting into a little bit more numerical analysis stuff. So today we're entering chapter 3. Let me just where's my brush palette here? Okay. Chapter 3. So chapter 3 is all about numeric summaries. Numeric summaries for data. Okay. So what is a numeric summary? Basically, let's just step back and think about what the big picture of statistics is all about. So in statistics, we start off with this large entity called a population. From that population, which is too big to be observed directly, so I'm just going to write too big, we take a little piece. Okay? We're just taking a little piece out of that population. We call this thing a what? Okay, yeah, this thing is called a sample. All right, and so our sample might have, for example, I don't know, n equal to 200 observations. Okay. And so our data table would have 200 rows in it. That still might be more information than we want to have to deal with, okay? So we saw last week a way to summarize some of this information using a frequency table or a summary table to summarize a bunch of observations. And today we'll talk about summarizing these observations with numeric summaries, okay? So we can summarize these 200 observations with a few numeric summaries. Okay, and so we have and so numeric summaries which are also called, if they're dealing with a sample, okay, can also be called sample statistics. Okay, so numeric summaries can also be called sample statistics. Summarize the data in our sample. Okay. And so, and these are very useful, especially when we are trying to make comparisons from one sample to another, okay? And whenever you see the word sample, you just think of one set of data, okay? So, here, I always talk about the population and a sample here, but really a sample can just be any data set, okay? So one data set and another data set. Okay, and so, oops, I didn't want to do that. Save as lecture 3. Okay. So, we are already familiar with certain summary statistics, okay? Some that we encounter in our lives today. So you guys are familiar with the concept of a GPA, all right? Okay. What a GPA is a single number that's supposed to summarize your academic performance, okay? Okay, so you can, instead of, if you wanted to compare one student to another student, you can look at their entire transcript. You can look at every single class they took, the grade that they got in, English, and the grade that they got in statistics, and the grade that they got in, whatever other class they took, okay? And you can do that, but then, if you have 30 students to compare, or, hundreds of students to compare against each other, it might just be it might be overwhelming to try to look at every single class that they've ever taken, okay? So a GPA is useful in that it summarizes the entire academic performance into a single number, and you can say, oh, this student has a 3.7, this student has a 3.4, this student has a 2.5, and then you can kind of just make quick judgments based on that, okay? And of course, we're all familiar with the shortcomings of using a GPA to try to summarize an entire student's life or student's academic performance, because it might not give you the details about their life. They might have had to work multiple jobs in order to get through college, or maybe someone else took easy classes, quote unquote easy classes. We don't know. Okay, but for example, a student with a 3.8 is typically going to be a student different from a student with a 2.5. Okay, of course we don't know all the details, but we can generally say there's probably some kind of difference between a student with a 3.8 and a student with a 2.5. Okay, so they are useful in making comparisons, but then if this is your sole thing that you are using to make comparisons, you are also missing out on other aspects as well. Okay, so that's the kind of the double-edged sword of using numeric summaries or sample statistics, is that they summarize a lot of data into a single number, which is very convenient and useful, but using that single number as the end-all be-all of everything is probably not wise either. Okay, so we have things like the GPA to kind of summarize academic performance. I'm going to flip over to the next slide here. And so we have other specialized numeric summaries. So if you want to know kind of a country's economic performance, you can use GDP, gross domestic product, or GDP per capita, which gives you kind of the relative economic power per person type of thing. In sports, so if you have if you're looking at the NFL, which is the football league in the United States, the kind of the leader of the team is the quarterback, and the quarterback, the performance of the team, a lot of it depends upon the quarterback, and so at the end of each game, the quarterback is given a passer rating, okay? So you have, passer ratings for quarterbacks, and this will tell you whether the player had a good or bad performance, but of course it doesn't tell you all the details. So maybe his offensive line was doing really poorly, and that's why the quarterback could not perform well. We don't know, okay? et cetera, et cetera, et cetera. Okay, so these are, you know, kind of like summary statistics for a specific purpose. Was that me? All right, we also have kind of these general summary statistics or sample statistics that can be used for any numeric data set, and they serve their own purposes. Okay, so we have kind of generic sample statistics. For any numeric variable. Okay, and so we have, and we can kind of split these into two broad categories. We've got statistics that summarize this notion of center or central tendency. And that would be things like the mean and the median. And then we have statistics for spread or dispersion. And this would be things like the standard deviation, and the interquartile range, and also the range. So these are numeric values for each of these things. I don't know how to change those lights there, but okay. And so the concept of central tendency is kind of you know, what are the, quote, typical numeric values? Okay. Or for spread or dispersion, this is, you know, kind of, are the values that we see, are they quite similar to each other, or are they quite spread apart? Okay. And these sample statistics can be calculated for any numeric variable, okay? Our textbook says that for certain situations, when our data is symmetric, we might prefer one set of numeric summaries or sample statistics, and when our data is skewed, we might prefer another set of sample statistics, okay? And there is truth to that statement or validity, but it's also true to say that these sample statistics can be calculated in either scenario. Okay. So so for symmetric data, and what does it mean for our data to be symmetric? So symmetric means that if our center is right here, values, I guess for your case, values much lower are about as common as values that are much higher, right? So symmetric data, this just means values much lower than, quote, typical So if you think of whatever is typical and you think of values that are much lower than typical, those values much lower than typical are about as common as values much higher than typical. Okay, and so for symmetric data, we might prefer, okay, to use the mean to summarize central tendency. And we might prefer the standard deviation. I'll write that out. For spread. Okay. And then for skewed data, and what does it mean to be skewed? So skewed means you might have extreme values in one direction, but not in the other direction, right? So skewed data, you might have values that are much higher than average or typical, but you're not going to have values much lower than average, okay? Or flip side, if you have left skewed, you've got values that are much lower than typical, but no values that are that much higher than typical. Okay, so that's what it means to have skewed data. So this is kind of like outliers or extreme values on one side, but not the other. Okay, so for skewed data, we might prefer to use the median and the IQR. But each of these sample statistics serve their purpose and can be used for any data set. I should say any numeric data set. So far, so good? Okay. Was that? Just one second. All right, no problem. All right, so I think you guys are familiar already with the concept of the mean. Like, you probably learned this in middle school or something. But we'll rehash it here, okay? So today I'll talk about the mean and the standard deviation, and then on Wednesday we'll cover the other ones, okay? Okay, so the mean. This is, you know, whenever we hear the term average, generally it's referring to the mean, okay? So average often, maybe not always, often refers to the mean, okay? But the term average is a bit ambiguous. It could refer to the median, so it's probably best to specify you're talking about the mean here, okay? And the symbol for mean is x bar, okay? And this represents the mean of a sample, or we call this the sample mean, okay, or the mean of a sample of data. Okay, when we talk about the mean of a population, which will come a little bit later in this course, we will use a different symbol, okay? But x bar, I'll write that. This is pronounced x bar. This is equal to the mean, and the formula given for the mean is sum of our x's divided by n. So this just means add up all of your x's. Add up the x's, okay? And then over n means divide by n. And then divide by sample size. Okay, and I think we're already familiar with this, okay? Perhaps a better conceptual definition, okay? So the conceptual definition of the mean can be thought of as the balance point of our data. Okay, so let's say we have a few values here, okay? So let's say we have, someone has 4 kids, okay, 4 children, and the ages are, we'll say you have a 2-year-old, a 4-year-old, a 6-year-old, and a 16-year-old, okay? All right, the mean age is equal to 2 plus 4 plus 6 plus 16, 28 divided by 4, which would be 7, right? Okay, so this is our mean age. All right, so visually or conceptually, we can think of this as, I'm going to create a number line here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, so I'm going to just create a dot plot here. And I'm going to make my dots extra large here. So I've got 2, 4, 6, and 16. Okay? So this is my dot plot. Imagine these, so I'm going to actually make these even bigger. Imagine these dots to be like stones, okay, or weights, or whatever you want to call it. All right? And imagine this thing being like a seesaw. Where would we want to put the fulcrum, or the balance point, okay? Well, in order for this thing to be balanced, what we're going to do is we're going to put the balance right here, okay? And so this here, this is the balance point. And our balance point is equal to 7, okay? So balance point at 7, this is where our mean equals 7. So this is what it means to be the balance point of our data. If we put the fulcrum here, basically this one weight on this side balances out the 3 weights on this side. Okay. Okay. And so in this case, is our data symmetric or skewed or what? Skewed into which direction is it skewed? It's skewed right, okay? And so because it's skewed right, this is actually a scenario where the mean might not be preferred to be used because, well, depending on who you ask, if you ask kind of like what's the typical age in this household, you know, perhaps it's better to use kind of the age that's in the middle, 5 or 6. You know, it's hard to say, okay? It's hard to actually, the question, what's the typical age of the kids in the household, it's a very difficult question to answer when the data looks like this, okay? And so the mean kind of gives you this balanced answer where, you know, only one child is older than 7, and you got the other 3 younger than 7, but it kind of gives, you know, 7 is not a very good answer for this question, but no other answer is really that great of an answer, okay? But here, you know, our data is right skewed, okay? So you have right skewed data. So, you know, it's hard to say, okay? You know, if we were in another scenario here, okay, you could imagine visiting a small town, okay? So we walk into a diner in a small town. Okay, and maybe in this small town it's like I don't know, I'm just making up a story here. Maybe it's like a small mining town, all right? And so almost everybody employed is employed by doing work for the mine company, okay? And so you walk in into the small diner and maybe there's 6 people there, okay? 6 people, and you want to know what is the average income? Average or typical income. Okay, so you ask the 6 people in the diner, how much money do you make? Okay, and maybe they all say, oh, I make $60,000. So the first 5 people you talk to all say they make $60,000. And then maybe one of them is kind of like the shift leader or something, and that person makes $70,000, okay? So then you say, okay, well, what's the average, the typical income? Average will be, we would say 60 times 5 plus, what's going on? 60 times 5 plus 70. We're going to divide that by 6. Well, that's not helpful. 61.67 thousand, okay? $61,667. Seems like a fair answer to the question, okay? I don't know. All right, so this is what we have, okay. Let's say Bill Gates walks in, okay? I don't know, who else has a lot of money? Huh? Yeah, I don't know. Okay, all right. How much does Bill Gates make a year? I have no idea.
His net worth is like $80 billion.
It's a lot. Okay, but I don't know what his annual income is. Well, now that he's like, I have no idea who pays him anymore. He's like found his primary job is his philanthropy organization, right? Okay, well let's just pretend he makes 10 million a year. I have no idea. I'm making that up, okay? So, okay, we'll just say super rich person walks in. He has an annual income of 10 million. All right, and then we have all of these people. All right. Okay, what is the average income now? Okay, so we're going to line these people up. What did I have here? Okay, so 370,000, these people all add up to 370,000, and then we're going to add 10 million, so that's, okay, that's that, and then we're going to divide this by 6, which is, again, okay, so now the average, the mean income is now $1,728,333. Okay. I don't know. All right. So would we say this is representative of the income Probably not, okay? And this is probably why we say for skewed data, the mean is not a fair value to use for the mean. I think there was kind of a case of this back in the day. I don't know if anything happened of it, but basically there was a small college that said our graduates make an average of $80,000 per year, okay? Which is like, oh wow, that's really good, okay? What they didn't disclose in that statement was that one of their graduates went up to became like an NBA pro athlete that made like several $1 million a year or something, and so that threw off the skew, okay? That skewed the representation. That's kind of like a silly version of this thing, but happened in real life. Okay, so, you know, would it be deceptive to say that? Yeah, probably a little bit deceptive. Is it technically wrong? No, it's not wrong, but it might not be the best best interpretation here, okay? But on the other hand, if I don't know, if you needed to disclose your company's expenditures, okay? And I don't know, this was a silly company, but okay, in this company you have 7 employees, all right? And 6 of them make, you know, between $60,000 and $70,000, and one of them makes $10 million. Okay, would it be fair to say, oh, you know, the average expenditure is really only like $60-something thousand per person, okay? Technically correct? Yes. Slightly misleading? Or a lot misleading? Yes, also. Okay, so basically, each of these statistics that we can use, and so the mean has its purpose, okay? And so the mean is a summary of central tendency, but we have to keep in mind that the mean is heavily influenced by extreme values, okay? So the mean is a value that summarizes central tendency, okay, and is influenced by extreme values. Okay, which depending on what you're doing, may or may not be the value you want to use. Yes, we have a question.
It's trivial, but we should have divided by 7, right?
Oh, I should have divided by 7. You are correct. Okay, so that does change it. Thank you. That's not trivial. That's crap. What was it? 10,370 divided by 7, which is, okay, 148142. Okay. Yeah. The point of my story is still valid, but the numbers definitely change. Yes. So we add these up and then divide by 7. Thank you. Okay. Good catch there. Okay, is that good? So that's the mean. We'll talk about the median on Wednesday, but I think you guys already know how the median works, but we'll make sure we talk about that also. Okay, let's talk about the standard deviation. Okay, standard deviation is a way to measure spread. Spread or dispersion. Okay. Perhaps it's easier if I talk about the variance first, and I'm just going to say the standard deviation is equal to the square root of the variance. So what is the variance? That's probably a better question. So the variance can be thought of as the quote-unquote average squared distance from the mean. Okay, so we'll start with that definition. We'll say the variance is the quote-unquote average squared distance from the mean. Okay. All right, so let's talk about this concept of spread or dispersion. Okay, so let's say I've got two families here. Okay, two families. Both families have we will say have 5 children. Okay, two families. Both families have 5 children, okay? And the average age, or the mean age, I'll say, the mean age of these children is 9 years old for both families. Okay, all right, so we will have the, what's a last name A? The Adams family, okay. All right, and so their kids, the ages are, we will say 7, 8, 9, 10, and 11, okay? And then the Baker family, okay, their ages are 1, 5, 9, 14, no, I'm adding that wrong, 13, and 17. Okay. So both families, 5 children, both families, average age of 9 years in both cases, right? Does life in the Adams family look similar to life in the Baker family? No, okay? So, you know, the Adams family, the kids were like boom, 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 boom. And, you know, you have 5 kids that are all, you know, very close to each other in age, right? It's, I don't know, maybe you knew some classmates in high school where you're like, oh, you've got a brother and you've got a sister, and they're like all very close to each other in age, okay? Whereas, you know, the Baker family, it's like this oldest child could almost be, you know, acting like a parent to the youngest sibling, okay? So all sorts of stuff. Okay, so even though to say, you know, there's 5 kids in both families and the average age is 9, it's not, it doesn't capture the whole picture. And so the key difference here is that the spread in the Baker family is much larger than the spread in the Adams family. Okay, so over here we have very high spread or high standard deviation, high variance, and over here we have low spread. Okay, so let's go ahead and we'll calculate the spread in the Baker family, and we can calculate the spread in the Adams family. Okay. All right, so what we're going to do is we're going to use this definition of the variance being the average squared distance from the mean. Okay. All right, so let's, I'm going to just flip over to the next slide. All right, so we'll say variance equals quote unquote average squared distance from the mean. Okay, so we've got the Baker family, and their ages are, I forgot, 1, 5, 9, 13, and 17, okay? It appears they really planned this out. Okay, so the mean age, all right, is 9, and we can verify this. We could add this up, divide by 5, and we would get 9. Okay. So what we're going to do is we're going to take the distance from the mean. Okay, and so we can say how far is 1 away from the mean. Okay, 8 years away. Okay, 5 is how far away from the mean? 4, right? 9 is 0. 13 is, these are not trick questions, okay? 4 and 8, okay? Is this okay? I mean, we could also, you know, just kind of subtract off 9 from each of these. Okay, if we wanted to, and we'd get -8 and -4. It doesn't really matter because the next thing it says, you know, what's the squared distance from the mean, right? So the squared distance, what is our squared distance? It would be 8 times 8, 64. 4 squared would be 16. 0, 16, 64, right? So far so good, if I'm talking about squared distance from the mean. Okay, so if we wanted to do the average square distance from the mean, I would add these up and divide by 5, right? So the average would be add them up, divide by 5. Okay, but I have like little quote marks around average, and that's because we're not going to add them up and divide by 5. We're going to add them up and divide by 4. Okay, we're going to add them up and divide by 1 less than our sample size. Okay, so the quote average here will be add them up, add up, and divide by n minus 1 rather than n, okay? And you know, someone's going to ask, why do we do that? Okay, well, the answer is it's complicated, okay? If you want to look it up, you can look up Bessel's correction, all right? And this is the reason why we use n minus 1 rather than n. You can go on Wikipedia and read this. If you decide to major in statistics, you'll learn why we do this, okay? But for everyone else, it doesn't really matter. Just know that this is what we do, okay? It corrects for this bias that forms if you don't use it. Okay, all right, so we add them up. Okay, what do we get? So we have 64 plus 16 plus 0 plus 16 plus 64, 160, and then I'm going to divide by 4. Okay, so we add them up. So I do 64 plus 16 plus 0 plus 16 plus 64. And then I'm dividing by n minus 1 rather than 5 or n. So I have 160 divided by 4, and I get 40. Okay? So this, my variance, is equal to 40. Yeah? So far so good? Okay, and then so the standard deviation is just the square root of that. So what is the square root of 40? It's 12.65. The standard deviation is 12.65. That's what we have here. Okay, so in the Baker family, the standard deviation is 12.65. This feels a little... Did I mess something up here? 4, 8, 64, 64 plus 16, yeah, 160 divided by 4. Okay, all right. Something feels a little off to me, but I feel like I did the math correctly. I didn't make a mistake somewhere along the way? Huh? I did the square root of 160. Okay, I was like, this, like, after you've studied, like, staring at statistics for a long time, you're like, certain things don't feel quite right. Okay, the square root of 40 is what I want. Okay, thank you. Thank you for pointing that out. Okay, yes, 6.32 feels much better. Okay, thank you. Okay, so my standard deviation is 6.325 there. Okay? All right, so we can do the exact same thing for the Addams family. I know we only have a couple minutes left, but you know, it'll take almost the exact same amount of time. So, or it won't take very long. So let's see. So we'll do this, and we're gonna just erase all of this stuff here. Blah. Okay, actually, yeah. Why did I bother? All right. Okay. All right, so the Baker family, what do we say? Or Adams family was, I forget. The ages were 7, 8, 9, 10, 11, I think. 7, 8, 9, 10, 11. The mean is 9, okay? So if we look at distance from the mean, we have basically 2, 1, 0, 1, 2, okay? So if we look at the squared distance, that's going to then be 4, 1, 0, 1, 4. Okay, so far so good. Okay, and then so quote-unquote average will be 4 plus 1 plus 0 plus 1 plus 4 divided by, rather than dividing by 5, we're going to divide by n minus 1. So I've got 10 divided by 4. So I have 2.5. So my variance is equal to 2.5. And so my standard deviation is going to be the square root of 2.5, which is 1.581. Okay, so my standard deviation okay. And so if we compared the standard deviation of the Adams family, which is 1.581, and the standard deviation of the Baker family, 6.325, okay, we can see that the standard deviation of the Baker family is much larger, actually 4 times larger than the standard deviation of the Adams family, okay? And you know, the way that we calculate the standard deviation, you know, if you look at the spacing out of the kids, right? The Adams family, the kids are all spaced out 1 year apart. In the Baker family, the kids were all spaced out 4 years apart. Okay, it's not a coincidence that the standard deviation for the Baker family ends up being exactly 4 times the size of the standard deviation for the Adams family. Okay, you don't have to know exactly how the math behind that works out, but you should know that the standard deviation is the square root of the variance, and the variance can be thought of as the quote-unquote average squared distance from the mean. Okay, we'll see you guys Wednesday.